Chapter 14 is about the sun. We are going to study the sun as an example star so that we can learn how stars shine. Isn't this a great image of the sun? When we look at the sun in different wavelengths, we can learn many different things. These wavelengths show us more about the corona and some of the activity on the sun, which we're going to talk about in this chapter. When stars shine, there's a balance of forces. We're going to talk about that. We'll talk about how they produce energy, how they transmit energy, and also about the atmospheric activity of the sun. We'll start with the balance. The sun is really big. It's really massive. And so it has a lot of gravity. Gravity pulls things in. So why doesn't the sun collapse? Well, there's another force that pushes against gravity, and that force comes from the gas pressure. So you've got gas pushing out, the gas pressure pushing out, and the gravity pulling down. This occurs everywhere on the sun, and it's called hydrostatic equilibrium. That's outside pressure. The pressure pushes out, and gravity pulls in. As we get deeper into the sun, you've got more material pulling down. So that means that gravity is stronger. So this means that the pressure also has to be stronger for the sun to remain in balance. Now, pressure is proportional to temperature. So if we increase the pressure, we will increase the temperature. This goes back to what we talked about. The temperature is a measure of the random motion of particles. So if particles are moving faster, they're hitting the walls of their container more often, which is providing a greater pressure. So increased temperature gives us increased pressure. It's not just the pressure that increases as you go towards the center. It's also the density and the temperature. And, okay. So you can see when we're at the center, the pressure is high, the temperature is high, as we talked about in the last slide, and also the density is higher. And all of these fall off as we get towards the surface. The sun produces energy in the core by nuclear fusion, which we are going to talk a lot about in the next slide. So it's producing all this energy, but it remains stable because the energy that is created is radiated away. and that's an almost perfect balance. Not quite. The sun is getting slowly brighter. So it's produced in the core, and then it goes through the sun, travels through the sun, which we'll talk about after we talk about nuclear fusion, and then it's radiated away at the surface. So what is nuclear fusion? Nuclear fusion is the fusing of nuclei. So an atomic nucleus consists of protons and neutrons. Protons have a positive charge and neutrons have no charge. And like charges repel. So when two protons come close to each other, the electrical force pushes protons apart. There has to be a force which holds the nucleus together. And that force is the strong nuclear force. It binds protons and neutrons together. Now, protons can only bind when they come really close to each other. Nuclear fusion requires slamming two protons together at high speed. Okay, high speed, you've got temperature is the measure of the average motion of particles. So if you've got high speed, that means you have high temperature. So you have to have a really high temperature. And these protons come moving very quickly, smash into each other, and they stick. If you've got slow-moving protons, as they come near each other, the positive charges repel each other, so they're pushed apart. But if they're moving faster, they can get closer without repelling. If they're moving fast enough, so at high enough temperatures, they can get close enough that the strong nuclear force takes over and is stronger than the electrical repulsion, and they can fuse together and they release energy. When they fuse together, this makes more massive nuclei from less massive ones. But we actually lose mass in the process. And this lost mass is converted into energy, which we will talk about in a few slides. Remember back to chapter 13 and the main sequence? What did I say about the main sequence? Stars on the main sequence fuse hydrogen to helium in their cores. So if they're on the main sequence, they fuse hydrogen to helium. This is called hydrogen burning. The sun is a main sequence star, so it also generates energy by fusing hydrogen into helium in its core. Let's talk about some of those nitty-gritty details. We start with 4 hydrogen nuclei. That's these right here. 1, 2, 3, 4. 4 hydrogen nuclei. And we end up with 1 helium nucleus. These are not the same mass. There's a tiny difference in mass. And Einstein figured out that mass can be converted into energy through the famous equation E equals mc squared. Or your change in mass equals the amount of energy divided by the speed of light. squared. This fusion process is very efficient. It only takes a little bit of mass to make a lot of energy. Fusion happens in the core because there it's hot enough to push the nuclei close together. It's 15 million Kelvin. At 15 million Kelvin, all the atoms in the core are completely ionized. So you've got a bunch of atomic nuclei floating around and a bunch of free electrons floating around. Now, hydrogen nuclei are the same as just single protons. So this hydrogen fusion process is also called the proton-proton chain. The first step in the proton-proton chain, or hydrogen burning, is that you take two hydrogen nuclei, two protons, and they collide and fuse together to make deuterium, to make a deuterium nucleus. So two protons collide. These two here collide. When they fuse, one of them emits a positron. A positron is like an electron, except for instead of a negative charge, it has a positive charge. It's called antimatter. It's the antimatter counterpart of an electron. So it has the same mass, same properties, except for the charge, the electric charge, is opposite. The positron bumps into an electron and they annihilate. That mass is converted into gamma ray photons, and that's what you see here. These squiggly lines leaving those are gamma ray photons. One of these protons, besides emitting a positron, has also emitted a neutrino. And when it emits a neutrino and a positron, it changes into a neutron. So now we have a neutron and a proton. This happens twice. So we end up with two deuterium nuclei. And then this deuterium nucleus collides with another proton. So you've got a deuterium nucleus plus a hydrogen, another hydrogen nucleus, and they collide together, and now we get a helium-3 nucleus. Two protons and a neutron. Helium-3 is what we call an isotope of helium. It has the same number of protons, but it has one fewer neutron than a normal helium nucleus. When these fuse together, we get another gamma ray photon that is released. The gamma ray photons produced here and in the previous step heat the surrounding gas. This energy eventually makes its way up to the surface. This step also has to happen twice in order to get one helium nucleus. So we had 4 protons collide to make 2 deuterium nuclei plus some energy. And then we add 2 more hydrogen nuclei, protons. They collide with the deuterium, and now we have H3. And then in the final step, You take those two H3 nuclei, fuse them together, and they kick off two protons. So we end up with a helium-4, a normal helium nucleus with two protons and two neutrons, and then these two protons get kicked off to fuse some more with other hydrogen nuclei. The energy produced in this step is in the motion of these particles. So all these things are moving, and that's kinetic motion, which translates to temperature. And now we're done. We started with four hydrogen nuclei, and we ended up with one helium nucleus and a bunch of energy. Here's some of the details. Four hydrogen nuclei weigh more than one helium nucleus. And so by a very tiny little bit. We can convert that to energy, plug in your numbers, and you get a tiny bit of energy. But the thing is, the sun burns a lot of hydrogen. It burns 600 billion kilograms per second. So this means that in a year, the sun loses 1.9 times 10 to the 19 kilograms. That's a lot of mass. It's all converted into energy. So now you know how energy is made, but it's stuck in the core. So how does the energy get out? Well, as it escapes the sun, it passes through a couple different zones based on the temperature and density. The first zone, the inner zone, is called the radiative zone. And that's where the energy is carried outward by radiation. And then it gets to this zone called the convective zone, where it's carried by convection. In the radiative zone, in the hotter part, you're going to have more photons in the hotter regions of the radiative zone than the cooler regions. So photons are going to be more likely to move from the hotter regions to the cooler regions than from the cooler to the hotter. So radiation works this way, works outward, carries energy outward from the sun, from the core of the sun. This is called radiative transfer. Energy escapes in the form of high energy photons radiating outward from the core. Now it's trying to get straight out from the core, but there's a bunch of stuff in the way. There's a high opacity. Opacity is a measure of how easily photons can flow through matter. And if you've got a very opaque material, this can slow it down. So think about a beach ball on the beach. If you've got a crowd of people playing with a beach ball, the ball isn't going to travel very far before somebody hits it and changes the direction. And so this ball will take a long time to go from one end of a crowd to the other end because everybody's hitting it back and forth and changing the direction a lot. This is also going to slow down photons. You've got a bunch of nuclei in this area, and these photons are going to bump into them and change direction. And so it's going to take a long time for them to travel out of the radiative zone. The radiative zone goes out to about 70% of the way to the surface. The temperature is still lower than the core, but it's still hot enough for atoms to remain ionized. Photons are scattered by electrons, so these photons bump into electrons and get scattered. So it takes 10 to the 5 years to reach the outer layers. Then it finally gets to the end of the radiative zone and gets to the convective zone. The temperature is dropping as we get further away from the energy producing core. The convective zone starts where the temperature is low enough that the nuclei, the ions, can capture electrons and become atoms. Energy is absorbed by atoms, and so they heat up. So the photons come through, and the light, the atoms, the electrons in the atoms, right, they'll absorb some of that energy by jumping up to higher levels, right? And then this heats up the atom. And what happens to hot air? It rises. So hot gas rises, and when it reaches the top of the convective zone, which is the sun's surface, it releases the energy as photons that radiate into space. Now it's lost its energy, so it's cold, and cold air sinks. And as it sinks, it leaves room for another bubble of hot gas to rise up in its place. You can see this in coffee when you add cream. Try it sometime. So take your coffee, add some, or tea, and add some cream. And don't stir it, but watch how the cold liquid comes up, kind of bubbles, and makes these nice little convective zones, convective bubbles. This is called convection. And you can see it in this picture. The centers of these bubbles, that's the hot gas. And you see the dark edges, that's the cool gas that's falling back down. So you've got the hot stuff bubbling up in the center and the cool stuff going down the side. Now, haven't you seen something like this in your coffee or tea? I think I've also seen it in miso soup. Now, I can't just say that this is what happens to the sun. We have to be able to test this. And we do. We test this in several different ways. One of the ways is using neutrinos. In step 1 of the process of the proton-proton chain, remember the protons, so you have two protons smashed together. One releases a positron and a neutrino and changes into a neutron, and then they become deuterium. Well, that neutrino is one way to test the solar model. Neutrinos are light particles, light atomic particles that have no charge, and they have very weak interactions with matter. So unlike photons, neutrinos can escape the core freely. We can measure the rate that they arrive at Earth and what types they are. So neutrinos can change flavors. For some reason we call the different types of neutrinos different flavors. Originally, we didn't realize that neutrinos could change flavors, so the rate that we were getting on Earth was only a third of what we predicted. And then we did some more theory and discovered, hey, wait a minute, there are different types of neutrinos, and they can change back and forth as they leave the sun. So once we started measuring all of the flavors of neutrinos, then we got a rate which agreed with our predictions. Another way to test the solar model of fusion is through helioseismology. Helioseismology is what it sounds like. So you've got helio, which is sun, and then seismology. Think about seismology on Earth, and we're talking about earthquakes. So these are sunquakes. You've got sound waves moving through the sun, and this makes the surface vibrate. And it vibrates at different frequencies based on the composition and the depth of the convection zone. We can tell how it's vibrating by looking at the Doppler shifts of the surface. So basically the interior of the sun is ringing like a bell as helioseismic waves move through it. This image is just one mode of the sun's vibration. The red gas, these red areas, that's where the regions, the gas is moving in, and the blue is coming towards us. Blue shifted and red shifted, Doppler shifts. That's how we're measuring it. And this is helioseismology. And this is a really good example of how our models change based on observations. Remember our neutrino problem? I didn't call it a problem, but I told you about it, that originally we only measured 1/3 of the neutrinos that were coming out. One solution to this problem was that there wasn't as much helium in the core, but through helioseismology, we realized, no, that's not a good solution because it doesn't match the observations. We also discovered through testing our models, through looking at observations through helioseismology, that our original value for opacity was too low. So we upped it to match with the reality of the sun. We can learn a lot from times when our experiments do not match what we think they should match. Like I said about the neutrinos, we didn't get what we expected. We have to have, the hypothesis was that the sun's energy comes from nuclear fusion, which produces neutrinos. And a specific number of neutrinos must be produced every day to account for the brightness of the sun. Well, we weren't measuring that. We were getting only a third as many neutrinos as predicted. So either we didn't understand nuclear fusion or we didn't understand neutrinos. So we came up with another hypothesis. What if neutrinos come in 3 different types and we were only detecting 1/3 of the types? So we put up more detection methods to detect the other types and discovered that yes, we did understand fusion correctly, and it was the neutrinos that we weren't understanding. So once we discovered the other types of neutrinos, once we started looking for other types of neutrinos, we found them and learned something new. Now we're done talking about the energy of the sun. Let's talk about some of the different layers. We'll start with the atmosphere. Now, the sun does not have a solid surface, but there is an apparent surface, and that's the point at which the light can directly escape into space. The layers above this point are what we call the atmosphere, and we can directly observe those. And so here's our sun. You've got the core, radiative zone, out from that, going 70% of the way to the surface, then the convective zone, and then we have the atmosphere. The apparent surface of the sun is called the photosphere. And it has a temperature, an effective temperature of 5,800 Kelvin, 5,780 Kelvin. As we go from the top of the atmosphere out, so from the base of the atmosphere out, the density drops very rapidly, and the temperature also drops. So the temperature goes down as we go out of the, as we go up from the surface, as we increase in altitude. When we look at the sun, the outer edges of the sun look darker. So it looks dimmer near the edge because on the edge we're looking into the sun at a steep angle, and so we're not looking deep into its atmosphere. When we look towards the center, we're looking face on, so we're looking towards the core, so we can see deeper into hotter, brighter regions. But on the edge, we're looking through less material, so it looks dimmer. The photosphere is cooler. So you've got these outer, cooler layers which absorb some of the light from the hotter, deeper layers. And our density has also dropped. So we get an absorption spectrum. And we have over 70 elements in the sun's atmosphere. This is a spectrum of the absorption spectrum of the sun. Above the atmosphere is the chromosphere. The temperature actually goes up in the chromosphere, so it has a higher temperature than the photosphere. And you've got a bunch of hydrogen there, and it emits red light. So it gives off a reddish emission line spectrum from hydrogen. Do you remember looking at hydrogen in the spectroscopy lab? That was that pinkish one. That's what we've got in the sun. So this red color, red pinkish color, is what gives the name to the chromosphere, to this region, because it means where the color comes from. The next layer up is the corona. And this is hotter than the lower layers. It's very hot. Talking 1 to 2 million Kelvin. It emits X-rays. It can extend for several solar radii. And the only time it's visible with the eye, well, the only time it's visible is when we block out the sun. We can do this with telescopes, where we just have a disk that will block out the sun and then we can see the corona. Or when the moon blocks it out for us during a solar eclipse. Did you guys see the eclipse? Did anyone see it? I did. I saw totality, and during totality I saw the corona. The sky was a deep dark blue and the sun was black, and then around it was this white material. It looked like tulle, like that material you use during a wedding, extending out from the sun. It was a really incredible experience. 2024 is the next total solar eclipse that is close to us. I strongly encourage you to make an effort to see it. So those are the layers of the sun. The sun's atmosphere is very active. And here's a picture of some of that activity, some of the coronal loops. Why is it so active? It comes from the magnetic field structure in the atmosphere. There are places in the atmosphere where the magnetic field lines can extend away from the sun, and those places are called coronal holes. And in these coronal holes, charged particles can flow away from the sun. This is called the solar wind. So you've got stuff spewing out from the sun, and while it's streaming away from the sun, the solar wind acts counter to the sun's rotation because it drags the magnetic field around with it. The magnetic field is wound up by the sun's rotation like water from a sprinkler. The sun is not stationary. It's moving. So as it moves, it blows a bubble that pushes interstellar gas out of the path of the sun's motion. So you've got all this interstellar gas, and the sun is moving through it, and it pushes it out of the way. This influence, this reach of influence is called the heliosphere. The solar wind pushes away material and helps protect the Earth from cosmic rays. Another cause is from what's called differential rotation. The sun is not solid. It's made out of gas. So it rotates faster at the equator than at the poles. The magnetic field goes through this material that's rotating faster at the equator than the poles, so it gets kind of pulled along and then gets all tangled up. And where it gets tangled, we get sunspots. Sunspots are cooler areas in the photosphere caused by tangled magnetic fields that trap gas at the surface, prohibiting it from sinking and warming. So we end up with cool gas at the surface because it can't get away because it's stuck in the magnetic field there. It's made up of the dark inner part called the umbra, and then the surrounding lighter part is called the penumbra. So you've got the penumbra on the outside and the umbra on the inside. These granules were what I was talking about earlier. I'm talking about convection. We have the hot gas in the center and then the cool gas around the edge. These granules are about the size of Texas. We can measure how much cooler, or how much less light they have coming out by knowing the temperature. So the amount of light that comes out per second per area, right, is called the flux. So the amount of energy coming out of a square meter of surface every second. Well, the temperature of a sunspot on the sun is about 1500 Kelvin less than the sun's surface. So you end up with the sunspot producing a flux that's about 32% of the flux of the sun's surface. Sunspots come and go in an approximate 11-year sunspot cycle. There's a solar maxima, and this is when you have the most sunspots. We're talking about the most sunspots in activity. And then there's a minima when there are not very many sunspots. So you've got a maxima and minima. So each peak is called the solar maximum. Between 1645 and 1715, there is a distinct lack of sunspots, and this is called the Maunder minimum. And it correlates to the mini ice age, which is interesting. I find it interesting how the sun, how the changes in the sun affect Earth. Our sunspot cycle comes to maximum every 11 years, but that's only part of a 22-year cycle. Every 11 years, the sun's magnetic field flips during the maximum of the sunspot cycle. So you've got at solar maximum, so you've got the south on one end, and then come the next solar maximum, it'll flip, and the magnetic south will be in the southern hemisphere, the magnetic north will be in the northern again. Sunspots come in pairs on the surface of the sun. And which one, so it has there's a north magnetic sunspot, and there's a south magnetic pole sunspot. And which one leads in its rotation around the sun depends on where the magnetic pole is. So during one cycle, the south magnetic pole sunspot will lead, and during the next cycle, the north magnetic pole sunspot will lead. We have more than just sunspots. There are also prominences. Prominences are hot rising gas in the chromosphere constrained by magnetic fields. You can see them here. And you have solar flares. Here's some prominences. Here's some good prominences. You also have solar flares and coronal mass ejections. Coronal mass ejections are highly energetic, violent bursts and eruptions. So you have a burst of mass coming from the sun, coming from the corona, so coronal mass ejection. These correlate with sunspot positions. The effect of this solar activity on Earth is called space weather. And this solar activity changes slightly over time. These solar storms can disrupt electric power grids and satellites, but they also cause brilliant auroras. I've never seen one, but I would like to. That's on my bucket list, to see an aurora. The problem is, in order to see an aurora, you have to go up to the poles. And I mean, you have to go up where it's cold. An aurora comes because of the interaction so the sun will send a coronal mass ejection or something. It'll have, you've got some charged material coming towards the Earth. Earth has a magnetic field. These interact, and when you interact, when these materials interact, that's when you get aurora. There's the aurora borealis in the north and the aurora australis in the south. These are actually mirror images of each other. I'm going to show you a planetarium show about them during lab. And now it's time for a quiz.